So picking up where we left off yesterday, we have the integral of cosine t. So you want to take the integral of cosine t. So the antiderivative of cosine is sine. So you get y equals the sine of t, and your upper and lower bounds are x squared to 2. So, fundamental theorem of calculus says, find your derivative, plug in the upper, subtract the lower. So you get y equals sine x squared minus sine 2. But am I looking for y? I'm looking for, okay, so the derivative of sine x squared becomes cosine x squared times 2x. Derivative of sine 2 is 0 because that would be a number. So, previously with the fundamental theorem of calculus, if you had a constant to a variable x, you just plugged the x in when you were trying to find the derivative of the integral. Now, the rule of thumb is if you have a constant to a variable that is something other than x, we need to incorporate the derivative of it. Because the derivative of x is 1, it really didn't matter. But now the derivative of x squared is 2x. So the derivative of y gives you that dy dx. The derivative of the integral really becomes the derivative of the bound times the cosine with the upper bound plugged in. So it's the upper bound plugged in times the derivative of the upper bound. And that's essentially the chain rule in reverse. So this is the chain rule for the fundamental for integration. Makes sense though, right? Next example. Okay, so we have the problem where it goes x to 5 of 3t sine t dt. So this is the case where the x is on the bottom. So we already kind of discussed this yesterday. What happens when the x is on the bottom? It switches all the signs, right? So it becomes negative. So then the derivative of the integral that is negative simply becomes negative 3x sine x. And again, this is, it's crazy, right? We're in integration, but this answer is a derivative. I've just thrown it out there that so you know the notation. Okay? The next example is a little bit trickier. It's very difficult at first to look at a bound where it's 2x to x squared. So what you can do is rewrite these bounds so that it's 2x to some number, because the number itself doesn't matter. Did I have to pick 0? Could I have picked 11? Could I have picked 100? Could I have picked 9? The answer is yes to all of them. The constant doesn't matter, right? Because it always zeroes out. Because the derivative of a constant goes away. So I picked 0 just because it's nice and pretty. So, if you try to find the derivative of an integral that is to a constant and a constant, you have to break it into 2 integrals. Because of the fact that the derivative of 2x is 2 and the derivative of x squared is x. So we break it into two integrals. Now, we know that integration bounds have to match. I can make them unmatching, though, if I want, by making this bound 0 to 2x, because I could simply flip them if I need it. We okay so far?
Mm-hmm.
So the derivative of the integrals then just becomes the function times the derivative of the upper bound minus the function times the derivative of the upper bound. Yes?
Why do you simplify the derivative of the upper bound?
Because of the example, if you go to example 8, so see how we, in example 8, that should be at the top of that page. It's the sine example. So do you see how when you did the sine x squared with the x squared bound, we actually integrated it and then we took the derivative? When we integrated it and took the derivative, you got cosine x squared times 2x. So when your bound is something other than x, technically you're multiplying by the derivative of the upper bound every time. It's just that the derivative of x is 1. So in all the previous examples we've looked at so far, technically you've been multiplying by a 1, but we just don't see it. If you think backwards, if I were to take, so this is the derivative, if I were to work backwards from this to get the original, that 2x has to cancel out with that x squared.
Well, why aren't you taking the derivative of the whole thing?
I did.
Well, when you have to use a power rule, or not power rule, quotient rule, or whatever it's called, because it's like division.
I never integrated.
I'm really lost right now.
The integral and the derivative cancel each other. They're inverse functions. I have to work out the whole problem. I need to see the whole.
I'm really lost.
Did you do okay on last night's homework?
Yeah, I got them all right.
So it's the exact same thing as last night's homework, except for on last night's homework, the bounds would have been 0 to x. Right? So then if you took the derivative of that, you just plugged the x in. The problem is this bound is no longer x. It's x squared.
Okay.
So now the bound is a nonlinear function. It's a quadratic. Quadratic function, by chain rule, has another derivative. It's 2x. So it's kind of like,
And you're plugging the x squared in 2x.
Just like you did yesterday.
Because those are the new bounds.
yep, just like yesterday. The actual plugging in part hasn't changed. What's changed is that the bound is no longer linear. A linear bound, so 0 to x, just like a 0 or a number, this, when you take the derivative of a constant, it becomes 0. When you take the derivative of x, it becomes 1. So it doesn't matter. Now our bounds are x squared and 2x. Well, the derivative of x squared is 2x. The derivative of 2x is 2. So those derivatives aren't zeroing out or becoming a linear function, or number 1. They're becoming functions themselves. So the derivative of the bounds is affecting the whole answer. Because if you work backwards, go back to 3x squared minus 7 to the 5th power. What do you have to do when you take that derivative? It's not sufficient to just say, oh, that's 5, 3x squared minus 7 to the 4th. What do you have to do? Because the inside derivative matters. Well, now the derivatives of these bounds matter. Because if I were to integrate this backwards, that 2x would cancel because it's like part of the derivative. Okay, I'm not going to do this one because it's gross. I will work out one of these really long. Again, not this one. This one's hard. Okay. Where's the... I'll work out this one because I know it'll be nice. Alright, find a bubble on your paper. Do a problem. Okay. Chain rule, quotient rule, all those rules tell you to work inside out, right? So if I gave you something that looked like this, you ignore the ddx and you do the inside. So what is the antiderivative of 1 over t?
Are you asking all of us?
Yeah, any of you? Yes.
Yeah.
So the ddx tags along, and you get ln absolute value t from pi to sine x. And then the rule of thumb is that you take the top minus the bottom. Okay? Good so far?
Why did you put absolute values on this side?
Now, we've done the integral part. Take the derivative. What is the derivative of natural log of pi? Well, ln of pi is a constant, because ln of any number is a constant. So the derivative of the natural log of pi, 0. Derivative of the natural log of sine x, well, the derivative of the natural log says it's 1 over u times u prime. What's the derivative of sine? So, the answer to this question right here is cosine over sine. If you apply the rule that I was just explaining to you, which is that you follow the FTC rule from the other day. You plug in the bound that involves the variable because the constant zeroes out. So this would become 1 over sine x. However, because sine x isn't linear now, this has a derivative other than 1. The rule is that you have to multiply by its derivative. The derivative of sine is
so it's just like a shortcut. It's basically that makes more sense.
it's like the chain rule of integration. That's what I was like that's like what I was calling it.
Yeah,
It's
that
just
makes
that
more
like you were
sense.
having trouble seeing it.
Yeah.
So like the general
And those are both negative, right?
so like the one NIMSY handout, they write it like this. So they say the derivative of the integral, and instead of calling it like I keep saying function, it's a function, x squared. They call it g of x. So g of x is any function, right? The idea is that this is really f of g of x times g prime of x. That is the FTC, because this is by technicality dy. So the derivative of the integral is the original function, change the variable, times the derivative of that bound. But like the bound of x, the derivative of x is always 1. So for like the first day, we never really saw it.
I feel like I'm cluster in my brain. Oh wait, I'm still in my notes.
I hate this problem. There's one like this once every 2 or 3 years on the
AP test, and there's a couple examples like this in our notes.
or in our book. So
Was that one last year?
I don't remember.
Was that one the previous year?
Yeah.
Well, then I think we're good. Yeah.
So it says construct a function of the form y equals a to the x of f of t dt plus c. Okay? So this is the idea that you have a function from, actually I think there's always one of these, it's just they mix it in different ways. So we're given the derivative of this function. We're given what? The derivative. So this is y equals all of that. If I took the derivative of this, I would get this, right?
Yes.
That's what FTC says. We are told that when y is 0, x is 8. So that's our initial condition. That's going to help me work towards finding c. What?
It just was reading really weird.
So here's what you're given from a to x of e of t dt, which we said this is the inside, because the derivative of the integral would give me this. Therefore, this is the inside. The only change is the bounds are t's instead of x's. Using our conditions, here's y, right? Y is 0. X is 8, so you're going to replace the upper bound with an 8. What am I needing or forgetting to include? The, yeah. So that's what we're working for. So, manipulate this. So this goes 8 to 8. We want 8 to x, right? That's the goal. We want a number to x plus c. So if we manipulate that so the bounds are 0, the plus c value here, in this case, had to be 0y. If you take the derivative of an integral from a constant to a constant, what's the answer? Take the derivative of an integral. Exactly. So if this is equal to 0, why does my c have to also be equal to 0? Because it's 0 plus 0 equals 0, right?
Yeah.
If this were to be equal to a number, then my c value would change.
So how do you know that's not equal to a number?
Because in the case of this problem, it's a constant to a constant. So the initial conditions started as a constant. If the initial condition here were something other than a constant, then it would change.
So then why is that one down there not x8 or 8 to x bounds?
So this is now saying we can find any y value that starts at 8, because the initial condition at 8 was 0. So now, like, this is like, Do you know the problems we did the other day where like it would tell you f of 1 equals 5.
Mm-hmm.
And then it was like find f of 3. You had to incorporate that f of 1, and we always started our integrals at the 1.
Yes.
And we added or subtracted that answer back in. That's the same idea here. They set it up a little bit different. And it kills me. I think the manipulation of it is hard for you to see, but conceptually you get it because you got it the other day. It's just, I don't like this. So what's the shortcut or the rule? We talked about this yesterday. Let's just review it. What's the shortcut?
Shortcut for what? That one?
If you have d dx as 0 to t of 3x squared dx, the shortcut is,
Plug in t for x.
and then if t was something other than a linear, you would have to
Multiply it by the derivative.
Derivative of an integral gives back the function. Derivative of an integral gives back the function. So capital F prime of x equals d dx from a to x of f of t. If the bound is something other than x, you have to multiply by the derivative. Man, I can't be PRT Friday. I'd go to Mrs. Potts's class. She goes, you have that on Friday.